All right, so here we see a series combination of a resistor and an inductor and a parallel combination of the same resistor and a conductor. So when we talk about impedance, the resistive component of the network or the actual resistor in the network is not always the resistive component of the impedance. If we're looking at the series equivalent series impedance here, right? So this Z in is going to be equal to our J omega L plus R. And then we'd write it as R plus J omega L to have our real plus J times the reactance. Um, so here the resistor in series will be the resistance of the series impedance. However, that's not going to be true in the pair when the two are in parallel. So let's take a look here. We can calculate our inductive impedance, which the reactance is the 4 radians per second omega times the 5 Henry. So it's J20. We can write that in rectangular form, or 20 angle 90 degrees if we want to write that in polar form. And in polar form might be easier if we're going to multiply it. So in series, our series impedance is 10 plus J20 ohms, where here equal to our R plus JX, it is in fact true that R is equal to 10 ohms, that's like the resistor, and our X is equal to that 4 radian per second times 5 Henry, which is just XL. And that's true because they're in series and we're adding them. But when we're considering the two components in parallel and we're trying to find this parallel impedance looking in, then we've got to take if we do the product divided by the sum, we get our R times our J omega L, and we'll write that J omega L now is in polar form is 20 angle 90 degrees divided by R plus J omega L, and we could write that as J20. So we can write this in our ZL is equal to 10 plus J20, but whoops, that's a 20, but it's also equal to our 20 angle 90 degrees. And sorry, our ZL is just equal to J20, right? ZL is just equal to J20. So we could write that as J20 as we did here, or 20 angle 90 degrees. So we'll do the product in the numerator in polar form, so we get 200 angle 90 degrees. We'll convert the denominator, since we had to add them, we'll convert them to polar form. So our 10 plus J20 is equal to 22.32 angle 63.43 degrees. And then when we divide 200 divided by 22.36, that gives us our 8.944, and 90 minus 63.43 gives us this positive angle. And then we can convert that back to rectangular form, and we can see here that this is the R plus JX, and this R, that ZR, right, that R is not equal to the resistance in the network, and the J4, that's not equal to the reactance of the inductor here. So we just have to be careful assuming that. If we wanted to look at the admittance of these two in parallel, or these two in series, or these two in parallel, well, the admittance of our inductor, we can write that as negative J over omega L, or negative J times 1 over 20 Simons. So that gives us a negative J.05 Simons, where our 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 B, that should be a B, so our BL is equal to negative 0.05 Simon, or equal to negative 50 millisimon. Or we could write it in our polar form here. So when we're working with admittance, we sum admittances in parallel, and admittances in series, again, we have to do the product divided by the sum. Or we could find the sum in parallel and divide that, or find Z and do 1 over Z, sorry. So our YL here is we can then populate in terms of admittance. So our resistance is resistive conductance is 1 over 10 or 0.1 Simon, and our inductive susceptance is 1 over 20 Simon. Sorry, having trouble with the vocabulary there. So then when we look at the two in parallel in series, we have to combine like like impedances in parallel. So we can prove that that's also equal to 1 over our series impedance. But in parallel, all we have to do is add them. So in parallel, we just add the admittances. So that's 1/10 plus 1 over J20, or we get 0.1 minus J5. So we didn't do this so much when we were just working with resistors. We didn't combine the resistors. Sometimes we did when we were doing current division. But certainly when we're working with imaginary numbers, and that's our complex impedances, then we want to work with admittances when we're working in parallel. So again, we add admittances in parallel. So if we look here at this example, we can say, this part is just our G. So here we have we get 1 over 5 Simon, which is what, 0.2 Simon. Here we get J omega C Simon, or equal to J times 500 kiloradians, so that's 5 times 10 to the 5th radians per second times our, that's 10 to the negative 6 times 10 to the negative 2 is 10 to the negative 8, so we get 8 times 10 to the negative 8 farads. So this gives us we get 40 times 10 to the negative 3 Simons. So if we're going to look at this parallel admittance, we just have 0.2 plus J 0.040 Simon, or it's equal to 200 plus J 40 millisimon. So that was pretty easy to do. If we want to look at the impedance, then we get to do it in parallel, or we could say it's just equal to 1 over y, so it's equal to 1 over 200 plus J40, and instead of millisimons, we can do, it's going to be kilo ohms, right? So we'll bring the milli up to the numerator. And then we can do that calculation. So when we convert this to polar form, we get, this is going to be equal to the square root of 200 squared plus 40 squared. So that's equal to, in my calculator, 203.96. So I'm going to have to write that out. 2 times 10 to the 2. So it's 203.96 angle 11 we'll just do 3.1 around that 11.31 degrees, and that's still going to be our millisimon. So 1 over that is equal to what's it, 4.903 angle negative now 11.31, negative 11.31 degrees. That's going to be the same, the angle. And this is times 10 to the negative 3, but this was kilo ohms, so we end up in we end up with that being in ohms. Yeah, so then we could also convert that to rectangular form. But it's easier again to find the admittance and then do 1 over that and convert to the impedance, particularly when we have a calculator handy.